Hello. Today we'll be solving a physics problem from the Introduction of Electrodynamics 4th edition written by David J. Griffiths, problem 2.16. We're told that a long coaxial cable carries a uniform volume charge density of ρ on the inner cylinder of radius a. So here's our coaxial cable. There's the inner cylinder within here with the cylindrical shell on the outside. We're told that this has a radius of a and a uniform surface charge density on the outer cylindrical shell of radius b. So here we have the radius b. We also take note that there is a length, but we aren't told explicitly how long it is, so we're just going to assume that it's extremely long, as coaxial cables are. So we're going to go ahead and just see that this is just a small portion of the actual length of the coaxial cable. So the surface charge density is negative and is of just the right magnitude that the cable as a whole is electrically neutral. We are to find the electric field in each of the three regions, the first being inside the inner cylinder, which we have here, between the cylinders, so in between the inner cylinder and the cylindrical shell, and 3 outside the cable, so outside the coaxial cable entirely. And then lastly, we're going to plot the electric field as a function of S. In order to do this, we are going to utilize Gauss's law, which states that the surface integral of E dot dA is equal to Q enclosed over epsilon naught. We can also call this the flux integral is equal to our total charge enclosed divided by epsilon naught. Just to make some statements on Gauss's law, it's extremely useful when there is symmetry that we can exploit. So, for example, spherical symmetry, in our case cylindrical symmetry, and then also a pillbox for planar symmetry. Since we're choosing a cylindrical Gaussian surface to utilize Gauss's law, we're going to note that the total flux integral is inclusive of both the integral of E dot dA of the curved surface plus the integral of E dot dA of the flat surfaces, which are perpendicular to each other, which means that this contribution is automatically equal to 0. So just to show you what that means, imagining this is a portion of the long coaxial cable, we see that these regions are completely flat. Since this cable is decently long, it is long enough that all the tangential components will cancel out and we are left with the field points in the radial direction. So parallel is going to give us stuff and perpendicular not so much. We start off with solving for the left-hand side of the equation, which is the surface integral of E dot dA. It's equal to the electric field multiplied by the area of our Gaussian surface. And in this case, since we're choosing A equal to the area of a cylinder, which is 2 pi s of L, where S is our radius and L is our length. Then from the right-hand side of our equation, we know that this portion is equal to Q enclosed over epsilon naught, and Q enclosed is just our total charge enclosed by our Gaussian surface. So we know that our Q enclosed is equal to our volume integral of our volume charge density. So when we take our volume integral, we have our volume charge density multiplied by pi s squared times L. So now we can put the left-hand side and the right-hand side together, and we can divide our area over to the right-hand side. So then we do our cancellation, and we are left with the electric field is equal to ρ over 2 epsilon naught multiplied by S in the S hat direction, when S is smaller than A. So when we're plotting the electric field as a function of S, we are also stating that C between 0 to A, which we're taking our Gaussian surface for, it has a linear dependency, so this is exactly what we expect. For the electric field between the cylinders, we choose a Gaussian surface to have a radial distance that's between A and B. That's to ensure that we're only computing the electric field between the actual inner cylinder and cylindrical shell. Still using Gauss's law, we see the electric field multiplied by our area is equal to the volume charge density times our volume over epsilon naught. And the reason why there is an A squared here is because we're looking for a charge enclosed, so the only thing that contributes charge is the volume charge density, not the free space. So if we're going to do the same steps and multiply the area over, we're left with ρ over epsilon naught times A squared over 2S in the S hat direction. So if we're to graph this, we notice that the electric field has a dependency of which is 1 over S. Since we're solving for the entire electric field between the cylinders, that means all the area between A and B, we expect a contribution of the electric field versus as a function of S to look something like this. So for Portion 3, there's a very important note about this. We are told that we want to find the electric field outside the cable. From the get-go, we're already told that in the problem, the cable as a whole is electrically neutral. Neutral is fine and dandy to just say that the electric field is equal to 0, but we're told that we have a volume charge density in here. The surface charge is negative and is the right magnitude, and the right magnitude just means that in order for these two sides to be equal, we would need to multiply the charge density by the volume, and the surface charge by the area is equal to this. The field outside is electrically neutral, which means this charge enclosed is equal to 0. So our electric field outside the cable is equal to 0. So last but not least, we're told to plot E as a function of S. So the electric field inside has a linear dependent on S, and the electric field between the cylinder and the cylindrical shell is a dependency of 1 over S. And then we have an electric field equal to 0 outside of that. So at this boundary, we drop instantaneously to 0. Thanks for solving the problem with me, guys.